So with refinement calculus. So as is known to all, the generative AI helps programming a lot, and there are multiple industrial products in generative AI and programming, like Copilot, ChatGPT, and Cursor. And we also see many applications in generative AI on theory improvers that translate the informal models to a formal data. And we use the GPT model, Ningbo, and the Copilot that helps the theory improvers. But there's remain a big question is that the GPT suffers the hallucination problems. So hallucination means that it generates plausible information but incorrect. So for example, a very basic algorithm like find a square root algorithm, the GPT-4 will generate a algorithm like that, and it will also generate the test case and test it online and say that it all gets passed. But it still remains a question whether this is a correct algorithms. It generates the test cases and persuades you that the code is correct. But if you look details, for example, you test the find square root of 5.1, it will go to an infinite loop. So if we go deeper about the algorithm, you can find that the x plus n divided by x is actually have a graph of this kind of shape. So when x is small, it goes to an infinite, and when x goes to large, it also goes to infinite, and the minimum number would goes to x equals to square root of x equals to square root of n. However, the x, because the guard combination is x squared larger than n, which means the x equals square root of n is hard to get. So in real world, because of the float precision error, so many test cases can be passed, but mathematically it is actually a wrong code, and in some test case it will go to infinite loop. So how we can give a correctness guarantee on the LLM-generated code? So we borrow the idea from the program refinement calculus, the Carl Morgan's versions. So the verifiable transformation of an abstract high-level formal specification into a concrete low-level executable program. So the previous square root example can have a formal specification like one precondition that for all input n that is larger than 0, and we want to find the x such that x squared is equals to n. So we can first go into a very simple example that we first find x such that x squared is larger or equal to n. So based on this precondition and the post-condition, there's many ways. And the large language model generates multiple code for that. For example, x equals to 1 equals to n equals to n plus 1. So we can find that some code is correct, can be verified by the automatic theory improver, but some can't. But formally, we can find that the x should be larger or equal to n plus 1/4. In that case, the x squared would be larger than n for all input n. And we can also verify that some algorithm like if n larger than 1, we can assign x equals to n, else we can assign x equals to 1. This is also a correct code, and it can be verified. So if we call back to the code large language model, so we reconsider the general code from the refinement logic, we can find that the generated code by GPT-4 is just follow this idea that when n is larger or equal to 0, it assigns x equals to n if n larger than 1, else 1. So in that case, we can have a post condition that the x squared is larger or equal to n. So how we can get the final post condition that is x squared equal to n? So we can split the post condition like x squared larger than n and x squared less than n. So we can find a clear structure of while loop that we first preserve the invariant x squared larger than or equal to n, and then we want to get a state that x squared also less or equal to n. So based on that, we can build the invariant and variant and build the while loop with the guard conditions. And the next question is whether the iteration is correct, whether we can terminate the iterations. So we have 3 conditions of the iteration. The first is that the invariant preserves. So that means the new x always preserves the invariant x squared larger than or equal to n. So we can verify it. And the next condition is that the variant is decreasing, which means the progress x minus this new x should be larger than 0. So which means the new x is always decreasing. And it also can be verified. So the last question is whether it can be terminated. So as I talked before, because the x squared is larger than n, so the new x is always larger or equal to n, which means the new x is always satisfy this while loop condition. So it will never terminate. So which means the program is incorrect. So a simple fix is that we just say we should not have a fixed point of x. The new x should always not equal to the original x. We want the x change. So that's the best we can get for the x. So our assumption is that the LLMs have good ability in program synthesis, in guess the code. So we try to find some ways, some formal systems to verify the generated code is correct. So for example, we can give the LLM with the precondition and the postcondition and let the LLM generate or guess the code. Then we can verify it, whether it is correct or not. So basically, we can guide the LLM with very basic laws. For example, the skip laws. If the precondition just implies the postcondition, it's just a skip. So if we can assign x as a variable x with an expression that makes the precondition implies the postcondition, we can just assign the variables. So it also has iteration, alternation, and the sequential composition laws to build the programs and then to guide the LLM to generate the code. So for example, still the square root algorithm, we have a formal specification that we now have an error bound E. So we want to find an x such that x squared is less or equal to n and x plus e squared is larger than n. So basically, we can split the postcondition into two parts. The one part is the invariant and the one part is the variant. That is the negative of the guard condition of the while loop. So in the first part, we can just first satisfy the invariant, which assign x with n plus 1. And then we can build the iteration with the guard condition that is negative this kind of condition and build the loop. Then we can try to verify whether this loop is correct. So this is incorrect because when x is very small, x is very small, for example, x equals to e fourth, which means the new x equals to negative 3 e fourth. So the x squared is actually increasing, so it will not terminate the loop. It is incorrect answers. So when we get an incorrect answer, we will have a fail feedback algorithm. So sometimes the ATP will generate some counterexamples to guide the LLM. Sometimes it will not, so the LLM will choose another direction to refine the specifications. So for example here, now the new invariant is x squared less than, which means we use this part as an invariant and the next part as a variant. So we can build the square root algorithm in a naive way. So we can also use another direction of refinement to build the square root algorithm with the binary search algorithm. We can say that we settle the upper bound and the lower bound with xy, and first assign the lower bound and upper bound xy, and gradually decrease the distance between the x and y, and finally achieve the guard condition. So we can reconsider these refinement laws. We will find that a big problem is that when we ask the LLM to find a sequential composition law, that means we want to find an intermediate condition to pave the ways for the future refinement. It was quite flexible. So the different laws have different flexibility. For example, the skip law is quite restricted. It must ask the precondition implies the postcondition. But for the sequential composition law, so it's not many constraints for this using this law. So a big problem is that how we can guide the LLM to utilize the sequential law correctly. So we inspired by the machine learning idea, so we learning the more advanced law from the data to make the formal system dynamically evolving. So remember, we have the different directions of refinement of square root algorithms. We can first assign the x equals to 0 that satisfies this kind of invariant. We can also use another direction that satisfies this part of post-cognition. So in this pathway, there's many data that follow the same pattern. First, utilize the sequential composition law, and then initialize the variant to initialize the variable to satisfy the invariant, and then build the iteration law. And the specification would also follow the similar patterns. So we can gather them and build a new law. Maybe we can call it initialize iteration law that first satisfies the invariant, and then we go to build the while loop to do the further post-cognitions. So the correctness of this new law can be constructed by construction, which means we can build upon the basic law like sequential composition law, assign law, and iteration law. So we can raise example for the learned refined laws. So for example, for the traverse law for the irregular structures, so initially, if we want to tackle some array structure, we need to first set the first element as the invariant and gradually increase 1. And this can be many steps, and you need to interact with many times. But we can then combine them together. That means we first initialize the variant, and we also set the iterations, and then also set the variant that is decreasing. So which means we can say that we only to have the next refinement on the PLI to PI plus 1. So for example, for the sort algorithms, so we can first define the formal specification of the sorted algorithm that we have a list such as this is a swap allowed list, and we want for all I, for all j in a range that Li always less than or equal to Lj. So we can directly use the traverse law to refine these specifications. And after use 2 times of traverse law, we can just remain the Li less than Lj. So then we can use the alternation law. If the Li less than Lj, which means we don't need to change the order. It's just the precondition imply the post-condition. We can just skip. If not, we just swap the element, and then we can get the basic sort algorithm, the bubble sort. So similar for the quick sort. So the quick sort is to find a k such that all the elements before the k is the sorted list, and all the elements after the k is the sorted list, and all the elements before the k is less than all the elements after the k. So we can just build a specification and refine them step by step. And with the advanced law, we can save a lot of time for refinement and proof. So the overall system is like, we first have an input that is human involved to generate correct formal specifications. And there's also many work in auto-formalization that interact with LLM to generate formal specifications. And then with this formal specification, we will choose a law by LLM and generate the corresponding code. And based on the code and the law, we will use the refinement module to generate the constraints to verify the code. We will use the automatic theorem provers with some SMT solvers to formally verify the code. If the code is failed to verify, we will send the feedback to the LLM to generate another code. But if it always fails, it will change it to a new law. And we will refine it until all the specifications get refined. So our program language is kept simple because the larger models is mostly familiar with Python. And our specification language also follows the Cork language. So we also have a specification building part because the specification may be complex, so we can split the specification top-down to some small specification and refine them one by one and construct program bottom-up. And we also use some real-world examples to instruct tuning the LLM with the refinement and the laws. So our results show that we can save much time and pass more test case, and we can show a more robust code because with ever plus data set that have more test case, we will not decrease the pass rate. So the limitation is that because we have a combination of specification, refinement calculus, ATPs, and LLMs, so we basically try to, based on the LLM, to build correctness guarantees for the LLM-generated code. But sometimes there are some components maybe not that good. We need to make some pattern for the ATPs to verify the code. And another problem is that we didn't have quantified the optimization problem. So we only try to synthesize algorithm, but not synthesize or optimize algorithms. There are many paths from the precondition to postcondition, but we didn't quite quantify which path is the best way. So in a summary, so basically we build a sophisticated formal engine to powered by the strong LLMs to automate the formal task, like the program synthesis. So that's all for my talk. Thank you.
Thank you for the talk. This is very interesting. One question that I had, probably taking a step back, is I guess finding the invariant and the variant is probably one of the most important things, right? So how are you going about it? I see that you've applied it on like the square root algorithm, the binary search quicksort, and all these algorithms. So if I had some other naive algorithm, how would I go about solving this problem?
You mean how to find the invariant and the variant?
Yes.
Yeah, because for example, in some cases the specifications contain is a conjecture form, so you can select one as the invariant and others as a variant. And you can also let the LLM generate the invariant and use the ATPs to verify whether it is the strengthened postcondition or weakest preconditions. You can also verify whether the invariant is correct or not.
So the language model is generating the invariant?
Yeah, the language model also can generate the invariant and the variant.
Okay, but okay. All right, maybe I can ask that question. Thank you.
Great. Let's thank, yeah, there's maybe time for one more question.
Again, thanks for the talk. One thing I'm not sure I totally understood, there you mentioned very briefly you had a slide about finding new laws for different data structures like the array. You had this traverse law. Are these laws you're kind of dynamically creating as part of the loop of inferring a program, or are they things you have to provide to power the inference right from the start?
So we dynamically involve the system. So after we have 100 examples, we'll check how much patterns in these examples, and then we create a new law for that. Maybe some typical patterns we can find from the laws. Yeah.
And does that require human intervention, or that's all done automatically?
It still needs human invention. Yeah, it will give some patterns, but you need to build the laws. I mean, you need to build the code for the laws. Yeah.
That makes sense. Thank you.
Thank you. Let's thank the speaker again.